Welcome to another Shock and Vibration webinar unit, and my name is Tom Irvine, and I'd like to again thank the NASA Engineering and Safety Center, NESC, and particularly Dr. Curtis Larson for sponsoring this series of webinars. Now, in the previous unit, we talked about Fourier transforms, and in this unit, we're going to be talking about fast Fourier transforms. And as you may recall, when we took a look at our Fourier transforms in a previous unit, we had an integral, and then the integral was changed into a series for the case of digital data. But there was a weighting function, and that was in terms of an exponential function. Well, it turns out for certain cases of time histories, there's some symmetry that occurs in the weighting functions, and there's ways we can combine steps to carry out the calculation in a much more efficient manner. And that is going to be the fast Fourier transform. Now, what we're going to find out is that if we have a time history that's maybe 10,000 points or fewer, or maybe even 20,000 points or fewer, it's probably a good idea to just go ahead and calculate a regular Fourier transform. But for larger time histories beyond, say, 10,000 points or maybe beyond 20,000 points, it's much more efficient and practical to calculate a fast Fourier transform. So let's explain these a little bit here. This is just something kind of cute. A number of years ago, these were popular. Maybe this is still going on. But the search for extraterrestrial intelligence at home, and this was sponsored by an organization in Berkeley, California. And radio astronomy data would be taken and fed into the volunteers' home computers. So when they were away from their computers, number crunching could be done on these signals to determine if there was any distinct spectral peaks that might be from an intelligent civilization broadcasting a communication signal. And whether the users realized it or not, the calculation going on in their home computers was the fast Fourier transform. So some of you may have seen these. So the discrete Fourier transform, that's what we derived in our previous unit, required a tremendous number of calculations, whether you realized it or not. So a time history with m coordinates would require m squared complex multiplication steps in order to calculate the Fourier transform. But the discrete Fourier transform can be carried out by a fast Fourier transform, however, and again that's by taking advantage of some symmetry in the weighting functions. So the fast Fourier transform could be performed if we have a time series with a number of points equal to 2 to the nth, where n's an integer. And the fast Fourier transform would accomplish the calculation in m log base 2m complex multiplication steps, where m is equal to the nth, where n is an integer. So if we have m is equal to 2 to the nth, where n is an integer, that is a suitable time history for which a fast Fourier transform can be calculated. Let's show an example. You're probably not used to dealing with base 2 logarithms. So let's say we have 1,000,000 points. This is our time history. The regular Fourier transform, the regular discrete Fourier transform, would require 10 to the 12th complex multiplication steps. That is a very large number. On the other hand, for our time history with 1,000,000 points, we could have, this would only require 2 times 10 to the 7th number of points. So thus the fast Fourier transform achieves the calculation in 1/50,000th of the time. So for this 1,000,000 point time history, the fast Fourier transform is tremendously more efficient. It's definitely the way to go. But I'm being a bit of a used car salesman here, and there's something I haven't told you yet, but I'm gonna confess now. So our fast Fourier transform is based on a time series with 2 to the nth coordinates, and if we have 2 to the 19th number of points, that's 524,288, or if we have 2 to the 20th number of points, that's 1,048,576. Well, unfortunately, our time history with 1,000,000 points falls between those two cases. So we cannot actually take a fast Fourier transform on exactly 1,000,000 points. We cannot do that. Well, we've got two choices, neither of which is the correct answer. Both have their own limitations. One is we can truncate our time history. So for our 1,000,000 point time history, we could truncate it to the 2/19th case. And if we did that, we sure are cutting out about half of our data, really. Well, that might be okay if we have maybe a shaker table test where there's steady state, random, broadband, stationary vibration. But there's a caveat there. We got to be cautious. The other choice is we could add trailing zeros. We could add, we call this zero padding sometimes. We could zero pad the time history so that in fact it has 2 to the 20th number of points. Well, the problem with that is that's going to kind of throw off our magnitudes a bit because we're adding some fictitious zeros to the data that are not actually there. Well, in this series of webinars, when we use the vibration data software, we are going to be using the truncation method from here on out. So an FFT can be calculated for time history with any number of the following coordinate pairs or data points. If we have exactly 2 points in our time history, we can calculate an FFT. If we have exactly 4 points, we can calculate an FFT. Likewise, if we have 8 points, or 16, 32, 64, and then so on. And then you can see these series of numbers here, each time going up by a multiple of 2. So these are the candidate time histories where we can do an FFT, and we can do it exactly without doing truncation or zero padding. So if you write your own signal processing software or MATLAB scripts or whatever, or do a lot of data processing and get into the details, these types of numbers, this series of numbers will become very familiar to you. And it used to be in the old days, 30 some years ago, if you went out and bought a spectrum analyzer, in many cases it would require and limit you to only measure time histories where you had 2 to the nth number of points for n's an integer, and it would do that by constraining both the sample rate and or the duration. So you had some choices how you set up the sample rate and duration, but the two working together had to give you 2 to the nth, where n's an integer for your time history. That way, when you got done capturing your time history, you could do an FFT without doing zero padding, without doing truncation. Well, that's kind of back in the olden days, and nowadays, of course, you go out and buy a data acquisition system, and you can get 10 megahertz or sample rate, or 10 million samples per second per channel, which is streamed to hard drive or maybe some solid state memory by now, and you can just take as much data as you want, almost as high as you want for almost as long as you want, and I guess you could get a terabyte of data collected if your hard drives had that much memory. Well, that's drinking water with a fire hose at that point. Well, anyways, let's move on. I think we've covered this slide already. So truncation, zero padding are our 2 options if we do not have exactly 2 to the nth number of points. Okay, we're going to start playing around with some data here, and we've got some data samples. And first of all, I'd just like to direct you to my blog, or at this point direct you to my blog. We talk about my blog a lot here. It's vibrationdata.wordpress.com. And I've got a section here called Webinars 6 and 7, Leakage Error, Handing Windows and FFTs. And some of the data samples that we're going to be using are already posted here. I need to post a few more things, actually. And some of these have corresponding sound files, either WAV files or MP3 files. And so kind of as a homework exercise, I want you to listen to these sound files so you can better understand our data reduction that we're going to do in our FFT process. And for a variety of reasons, I'm not going to actually do this in this audio-visual file, but I'd like you to do that on your own. And by the way, anytime you're at the blog and you just want to see what the webinars are, just type in webinars in the search box here, and you can see the various ones. The future one after this will be waterfall FFTs, but today we're on the FFT audiovisual presentation webinar. Okay, so let's go back. We've got a file that's called panel.txt. It's got 2 columns, time in seconds, acceleration g. It was measured on the front panel of a semi-trailer as it was driven over a test course. It was a proving ground. The data has exactly 2 to the nth power points, and it comes out to 8,192 points. Conveniently an integer power of 2. The battery-powered data acquisition system forced that. So we're going to do an FFT. We're going to do both a Fourier transform and an FFT on this data called panel.txt with 100 Hertz maximum plotting frequency. So we're going to compare the results both from the Fourier transform and the FFT, and we're going to do that both for speed and accuracy. So I'm going to type in vibration data. This is our main GUI package. It's up to version 4.1 and rising. So please visit my blog periodically to download the newest version. By the time you actually access this audiovisual file, this could be up to 5 or 6, or who knows how high it will be. So let's just do a Fourier transform, begin signal analysis. This input array must have 2 columns, time in seconds and amplitude. External ASCII file, panel.txt. Maximum plot frequency, 100 Hertz. Acceleration G will be the Y label. Let's calculate. It'll take a number of seconds to do a Fourier transform. Not too bad, but it did take a number of seconds. Backing up, here's the actual time history that we're taking a look at. 4-second duration. We're not so much interested in the phase angle, so I'm just going to delete this plot. And here we see the Fourier transform magnitude with a peak at 17 Hertz. So what I'm going to do now is I'm going to copy this figure, and I'm going to go to, maybe I can just do a WordPad here. So I'm going to go to WordPad, New. So here is a regular Fourier transform of the panel.txt data represented in terms of acceleration G, frequency in Hertz with a peak at 17 Hertz. Okay, now the next thing we're going to do is we're going to go back to the main GUI window. We're going to do an FFT. And I want you to notice how much quickly the FFT runs. As I push buttons, we'll get the results almost instantaneously. It's going to be the same file. It's panel.txt. Now this file only has 8,192 points in it, so doing a Fourier transform is not so bad. But if I had 1,000,000 points or whatever, it would take an extreme amount of time to accomplish that. So let's do 100 Hertz will be the maximum plot frequency. Again, acceleration G. I'm going to push this calculate button, and it's going to be almost instantaneous. See? Again, we're not interested in the phase angle plot. Here's the time history. We've seen it before. It looks like there's kind of some couple of sinusoids buried in there, dominant sinusoids. In fact, we see that. There's a 17 Hertz and then maybe 19 Hertz, 21 Hertz. We get a cluster of spectral peaks there. Now, this figure here is the fast Fourier transform. Even though the title says Fourier transform, more properly, it's the fast Fourier transform. Over here on the right side is the regular Fourier transform, and those two plots are identical. And the reason they're identical is because in this case there was exactly 8,192 points, and that's equal to 2 to the nth, where n is an integer. I'll let you figure out what that integer is yourself. If the time history had only been 8,000 points, or if it had been 9,000 points, we would have been doing some truncation to do our fast Fourier transform, and then potentially you'd have seen some slight differences in the data. Potentially. Okay. We're going to move along, and we're going to do an exercise that is very fun. This might be one of the funnest exercises we do in this class. We're going to look at a piece of data, and this is going to be an Apache helicopter flyover. So here we've got an Apache helicopter, and this is going to be an audio recording, and we're going to take the FFT going up to maybe 1,000 Hertz, or maybe only to 500 Hertz. We'll use mean removal and handing window. I'd like you to separately listen to the sound file. It's really interesting. We want to find out a couple of things from the data. We want to be able to deduce what is the main rotor hub frequency and what is the tail rotor hub frequency for the Apache helicopter. So let's go ahead, and we're going to go to our vibration data package again. And we got a couple of things we can do here. Let's go to plot utilities. We're just going to plot the time history. It's going to be apache.txt. This is unscaled sound pressure. So this was a sound file that was converted to ASCII text format. And I actually should put that over into the y-axis label. Title, Apache helicopter, flyover, flyby, whatever you want to call it. So here's our unscaled sound pressure versus time for the Apache helicopter flyover. So if we kind of zoom in on some of this data here, draw the window, one of the things we want to do in this course is to develop some critical thinking skills. And we'd like to look at signals and see what's going on. Is this a random vibration? Is it a half sine pulse? Is it a beat frequency? Is it a damped sinusoid? And it's kind of hard to tell, but I kind of get the idea just looking at this time history. There may be a pattern of sinusoids in there, embedded in there. Well, how can we figure that out? How can we resolve that? Well, we've got this marvelous tool called the Fast Fourier Transform. So let's go to our Fast Fourier Transform tool, begin signal analysis, external ASCII, apache.txt. We'll go ahead and do mean removal, yes, handing window. Got unscaled sound pressure. Let's plot up to maybe 500 hertz. And here's our FFT. Again, in this case, we're not interested in phase angle. I'm just going to delete out of that. The first figure is the time history. We've seen that before. It just gets repeated. So here's what we want to do now. We want to look at these spectral peaks, and we want to. It turns out there's a pattern of sinusoidal peaks that are manifesting themselves in the frequency domain. So what we would want to do at this point, in fact, I'm going to just sort of narrow down a bit more on, and I'm just going to plot up to 200 hertz. So here we have our spectral peaks up to 200 hertz. So let's go ahead and do some data cursoring here. We're going to identify the frequencies of the spectral peaks. So I have a spectral peak at 42 hertz. Now there's a way we can do multiple data cursors displayed. It's called, what's it called? It's create new data tip. Okay. So I've got one at about 51 hertz. Well, this next one here, let's see what we can do to identify it. Oops. Okay, I'm stumbling around a little bit. Let me tell you what, I'm going to do this just a little bit different. I'm going to just give me another chance at this. I'm just going to pick out a certain pattern of peaks because I kind of know ahead of time what's going to be happening with this. So let's pick out this one here. Fumbling around here, if you'll be patient with me. Okay, we've got a peak at 42 hertz, and then our next one is actually going to be at 63 hertz. And if I do create new data tip, I can show you the one at 84 hertz. And then we've got one at 104 hertz. So do create new data tip. 105 hertz. And this one here, okay, now I'm doing a little better here. So now I'm going to create yet another data tip. Okay. I've got a pattern of spectral peaks here. 42 hertz, 63, 84, 105. We'd like to round off in this course. So what's the pattern there? Well, there's a pattern at every 21 hertz. At every 21 hertz, we get a spectral peak. Well, let's see. Is there a spectral peak at 21 hertz then? Create data tip, and if I go down, let's see if we can pick up. Yeah, it's a bit faint, small magnitude, but there is a spectral peak at 21 hertz. So is that a clue? Is the fact that we have spectral peaks at every 21 hertz a clue to what's going on? In fact, I can do a create new data tip, and I can go up and say, I bet there's one at 126 hertz. And in fact, yeah. So a pattern of 21 hertz continues on. We could go up to much higher frequencies. So this is a big clue. So our question is that we want to resolve, and let me pull up a little WordPad here just to show you what's going on. Again, if you'll be patient with me. File, new. So we have a pattern of peaks at 21 hertz. That's our pattern. So our question is, what is the main rotor hub frequency? Now, a lot of times when I do this in a live course, here's what students will do. I'll ask this question, and they'll say, okay, the highest spectral peak here is at 153 hertz. So a lot of times students say, well, 153 hertz must be the main rotor hub frequency because that's the highest peak. Does that make sense? Well, what is the tangential blade tip velocity? So for an Apache helicopter, the blades sweep out a radius. So you can see the blade length is equal to 24 feet. And our tangential blade velocity is going to be omega times radius. And omega is going to be 2 pi times the frequency in hertz. So is it possible that 153 hertz is the main rotor hub frequency? Well, if we go to vibration data, we can go to a little utility here, miscellaneous function, rotation. We can do tangential velocity. So we have a 153 hertz, that's our highest individual spectral peak. Radius 24 feet. And that's equal to over 7,000 meters per second. Well, does that make sense? And the answer is no, that does not make sense, because the speed of sound is 343 meters per second. And I think we should have a requirement here that our tangential blade tip velocity must be subsonic. Otherwise, shock waves would form. And if shock waves form, that would interfere with control algorithms, because those blades are on actuators, so they can be bent and raised and lowered and twisted and all sorts of things to control the direction of the vehicle. Also, if there were shock waves forming, there could be some fatigue and structural damage occurring as well. So the blade tip velocity must be subsonic. So the other thing students oftentimes will assume is, well, we've identified a 21 hertz pattern, so that must be the blade tip, the main rotor hub frequency. If we go back here, type in 21 hertz. Well, again, the speed of sound is 343 meters per second. That's, sea level, normal atmosphere type day. So we're almost 2.5 times, almost approaching 3 times the speed of sound if our hub frequency, main rotor hub frequency, is only 21 hertz. Well, here's what we have to realize. What we're actually picking up, the 21 hertz pattern, is actually the blade passing frequency. And it turns out for Apache helicopter, there are 4 blades for the main rotor, which means the main rotor hub frequency is equal to 5.25 hertz. And that's from our measured data. So how can we check this? Is there a way we can validate that? Is there any independent check we can do? Because this is just measured data. So we have our empirical data, and based on our empirical data, we set forth a hypothesis, if that's the right term, or a preliminary conclusion that, in fact, the main rotor hub frequency must be 5.25 hertz. Well, how can we check that? Well, it turns out there's the United States Department of Defense has published a MIL Standard 810, and it's up to Rev G, or maybe by the time you read this these slides or view this presentation, it'll be up to H or I or whatever. But now the Apache helicopter is not listed by name in Mil Standard 810G, but it is represented in terms of model number. So AH64 now is our measured data from an early helicopter or late Apache helicopter? I don't know. So we're just going to split the difference and say the main rotor hub frequency should be 4.84 hertz. 4.84 hertz, huh? Well, so here we have 5.25 hertz from our measured data, but the published Mil Standard data is 4.84 hertz. Again, I'm splitting the difference. So it looks like we're off by about, I think that's about 10% or so, whatever percent that works out to be. We have, so what's wrong? Do we have an error here? Is there an error in the way we take our Fourier transform? And just for, I want to go back and sort of double check myself on a statement here. Sometimes I go along talking too quickly. Let's go ahead and see what the percent difference is. So if I have 5.25 and I subtract out 4.84 hertz and divide by 4.84 hertz, okay, that's actually going to work out to be 8.47%. That's a percent error. So why do we have that percent error? And it turns out there's a very simple answer that some of you probably already realize, and that is we have a Doppler shift going on. The helicopter is approaching or flying towards the ground receiving station, so the acoustic waveforms become compressed and the apparent frequency rises. So we have a Doppler shift going on. So let's think about the Doppler shift. Well, we got to do a couple things first. First of all, what if we have 4.84 hertz or 5.25 hertz for our main rotor hub frequency? So I'm going to type in. I'll put in our measured data 5.25 hertz. That being the case, we have a velocity value. Excuse me. Okay, let me back up here a little bit. .25 hertz, 24 feet. Okay, need to get all my data entry correct. Okay, if we have 5.25 hertz as our main rotor hub frequency, then the blade tip velocity would be 241.3 meters per second, and that is subsonic because the speed of sound is 343 meters per second. So we've met our constraint that the blade tip velocity must be subsonic. So the next question is, how fast was that Apache helicopter approaching the ground station? So if we go back to our slides here, probably in high school physics you learned about Doppler shift. So our measured blade passing frequency is 21 hertz. The apparent main rotor hub frequency is 5.25 hertz. The actual main hub frequency from the authoritative Mil Standard is 4.84 hertz approximately. So what's the estimated speed accounting for Doppler shift? So there's different types of Doppler shift formulas you probably learned in high school physics. The frequency shift, the shift between those two frequencies, is equal to the difference in velocity between the receiver relative to the source divided by the speed of sound c times the reference frequency, which is the actual hub frequency, in this case f sub 0. So delta f is equal to f will be the measured f minus the reference f here. So and there's other ways we can rearrange this algebraically if we need to calculate the delta v or whatever. We can do our algebraic type manipulations. And that's a good homework exercise, but I'm going to show you right now just a little simple way of doing this, because we can go back to vibration data. We go to the acoustics here, and we go to miscellaneous. We actually have a Doppler shift option built in. So our speed of sound, the equivalent in English units is 1120. Or in terms of miles per hour, our speed of sound is going to be 767 miles per hour. We want to calculate the source velocity. The source frequency, the actual reference frequency, is 4.84 hertz. The apparent or measured frequency is 5.25 hertz. We're going to assume that the ground monitoring station was fixed to the ground, so there was no receiver velocity. So in this case, the source velocity, now this is the Apache helicopter approaching the receiver. When I say receiver, I mean the microphone / data acquisition system. That Apache had a velocity of 60 miles per hour, which is plausible because the top speed of the Apache would be much higher than that. But 60 miles per hour is a very plausible value for the speed. And this exercise we're doing now, we're kind of doing it as a homework exercise. But this is the same exercise that I went through when I first encountered this data. But we're not done yet. We have something else to do with our Apache data. So what about 153 hertz? What is that due to the main rotor or not? So what if we have 21 hertz, that's our blade passing frequency for the main rotor, times 6. Okay, 6 here, that's the 126 peak, the little data cursor thing. Readout disappeared, but this is the 126 hertz peak. What's the next one up in this series of integer harmonics? 147 hertz. Well, this peak is 153 hertz. There is a peak at 147 hertz. What's the next one up after that? 168 hertz. That's this spectral peak here. Well, so by just sort of some deduction and process of elimination, I think what we're going to have here, I'll make a hypothesis that 153 hertz is due to the tail rotor. So could that be so? Well, how could we check that assumption here? Well, let's go back to our authoritative mill standard and see what that has to offer to us. So mill standard says, if we take a look at this, that the Apache helicopter for the tail rotor, again we're going to have to split the difference here. The rotational speed for the tail rotor is about 23.5 hertz, and there are 4 tail rotor blades. Now, we have to apply a Doppler shift, so we have to go up by about 8% or so. So I'm just going to sort of kind of tell you that I think that after we account for Doppler shift, we've got about a 25.6 maybe hertz for our blade passing frequency for tail rotor. And maybe what we really ought to do is just go back to our data here. And let's see. Is there anything going on at 25.6 hertz? And the answer is no, because that's going to be the hub frequency. And the hub frequency by itself doesn't really cause much, if anything. But the blade passing frequency will. And this is going to get a little bit tricky. There's 4 blades, but it turns out that the blade passing frequency, I'm going to kind of give this away a bit. The blade passing frequency for the tail rotor of the Apache helicopter is actually going to be a multiple of times 2 rather than times 4. I'll explain that in a minute. So let's see if we have a times 2. Okay, so what am I going to have to do here? I'm going to have to do a reset view, I guess. And let's see what's going on around 50 or so hertz. So tool, let's do a data cursor here. Okay, it comes out to be 51 hertz. So the blade passing frequency, which is going to be a times 2 multiple, is going to be 51 hertz. And I guess that's actually going to put the hub frequency down at 25.5 hertz. That's the tail rotor hub frequency. So if we have 51 hertz and we take the times 3 integer multiple, that's 153 hertz. Well, if I do a tool reset view, that's the spectral peak here at 153 hertz. That's the highest spectral peak in terms of magnitude. The highest magnitude spectral peak, that's 153 hertz. So why did that happen at a minus 2, excuse me, a times 2 rather than a times 4? And this is an interesting thing about the Apache helicopter. We have to look at the tail rotor of the Apache helicopter and see what's going on with that tail rotor. Is there something odd about that? There are 4 blades, but they're not oriented at 90-degree angle separations. Rather, we have the small angle here is 55 degrees, and then if we take the supplementary angle, that's equal to 125 degrees. And for some reason, this unusual arrangement is required because the 2 sets of blades use a delta hinge, and that delta hinge allows the blades to simultaneously flap and feather. And it appears just from our data that the 4 blades are acting as just a pair of blades, in other words, as 2 blades for the purpose of sound and vibration. So you might ask yourself also, why is the highest magnitude occur at a tail rotor rather than the main rotor in terms of blade passing frequencies? And a couple reasons. The main rotors are churning up all this air. There's different wake turbulence, there's trailing vortices, and all these things going on. And we've got this tail rotor slicing into this churned up air. And also we might think about it, there's something called a directivity pattern, and the main rotor is going to be roughly horizontal to the ground, or maybe even perfectly horizontal to the ground. So that has one sort of directivity pattern, but this vertically oriented tail rotor is going to have a directivity pattern that's going to yield a more direct and a stronger transmission path to the ground as well. So those are the 2 reasons why the tail rotor has the highest individual spectral frequency. And why did that happen at the -3 multiple? I'm not sure. I'm sure there's some acoustic theory that could account for that. Okay, so that's enough for the tail rotor frequency, the Apache helicopter. And so what we found out is the Fourier transform is a wonderful tool for kind of being a data detective and figuring out what was going on with the Apache helicopter. And now we know a lot more about Apache helicopters. So we've done this for an Apache helicopter data, but this could have been done for an automobile or a launch vehicle or a machine tool or whatever. Whatever you might have that has any sort of harmonic peaks or distinct spectral frequencies of any kind. So what we have to do is we do different things. We look at the time domain and kind of get an idea for qualitatively what's going on. We might look at histograms sometimes. And then we like to identify what the frequencies are. And there's time domains, methods of doing that we've already covered. There's frequency domains like Fourier transforms and Fast Fourier transforms. And once we've identified what the frequencies are, then the next task is to determine what do those frequencies represent? What is physically going on to cause those frequencies to occur? And those frequencies, that energy can be forcing frequencies, or it can be natural frequencies excited into a resonance or whatever. But we have to be data detectives, and we have to go out and sometimes gather further information, like looking at that mill standard as we did, to try and determine and identify what is going on with our data. So I'm going to now take just about a 30-second pause and get a drink of water. And when we come back, we're going to be looking at another set of data from a transformer box. So hold on, please. Okay, maybe you have one of these in your neighborhood or near your home or apartment complex, wherever you might live. And this is a transformer box. It's a utility box. And if I understand correctly, the power plant is where the electrical power is generated, and it has a high current, and it has a low voltage at the power plant. Well, in terms of sending that power over the transmission lines, it's advantageous to reduce the current and increase the voltage. And that is done by a transformer at the power plant. So then this low current, high voltage power is sent into your neighborhoods or near your office, wherever you might work, or the stores that you may shop at. And there's another transformer. So I'll call the one at the power plant the step-up transformer. I'll call this one near your home the step-down transformer. And what it does is it's going to reduce the voltage and increase the current. And it does that because that's more efficient for powering up all of your air conditioning unit and your refrigerator, all of your appliances, your lighting, whatever. So that's sort of a probably oversimplified explanation of how power gets transmitted. Well, it turns out these things, if you ever walk by one of these at night, maybe it's a quiet night, it's late at night, and there's no traffic noise, there's no dogs barking, you'll hear a buzzing sound. And we're going to look at an audio recording of a buzzing sound. And what we want to find out is what kind of spectral components are contained in that data. Well, the electrical power that comes in, now I'm talking about the United States here. In the United States, the electrical power is at 60 hertz. That's the frequency of our electrical power. So we might expect then to get an audio signal in that buzzing at 60 hertz, as well as integer multiples thereof. So let's see if that's going to happen. So let's go to, we're back to our vibration data, our GUI package that we like to run here. And I'm going to just take a look at the time history, plot the time history, external ASCII file. This is called transformer.txt. It's just going to be this transformer audio signal from the buzzing. Y-axis, this is another one of those files where we have unscaled sound pressure. So here's our signal here, unscaled sound pressure versus time from the audio recording. And as we zoom in on it, is this random? Is it broadband random? Is it white noise, pink noise? Is it a damped sinusoid? Is it a beat frequency? Is it... Well, it does look like there's some repetition going on, so there's some kind of pattern. There's definitely more than one sinusoid, which actually we would expect that, but there's some sort of repetition going on. So how do we resolve that repetition and identify those spectral peaks? So we're going to take a Fast Fourier transform of the transformer.txt data. We'll plot up to 500 hertz in this case. Mean removal, yes. Handing window. Okay, we're good to go. Phase, we're not going to be interested in phase. Time history, we've actually seen that before. So, what do we have here? What kind of spectral peaks do we have? Well, let's just take some of the dominant peaks here. So I'm going to take a data cursor here, and well, it's occurring at 121.7 hertz. Let's create a new data tip. What's this one out here? 365.4 hertz. What about this one out here? Create a new data tip. 487 hertz. Well, what about some of these others? Let's see. What about this one right here? Create new data tip. Now, I actually took this just using kind of an old-fashioned analog tape recorder. So there could have been, and then I digitized it by playing back the tape recorder. So what we actually here, we're going to round off and say maybe there was a slight bit of frequency shift in our data. And I'm going to say that the pattern here, the first peak is actually at 120 hertz. And then the second peak is actually 240 hertz. And then 360 hertz. And then 480 hertz. Okay, I'm obviously doing some rounding off here. And so this is the pattern of peaks that we end up with. So the question is, where's our 60 hertz signal? So if we go back and look at our peaks, is there even something at 60 hertz? Well, let's see if we go to create new data tip. Well, kind of, sort of, maybe there might be something down at 60 hertz. Let's see. Yeah, that one's 63 hertz. Really not much going on down at 60 hertz. So our 60 hertz component is missing in action. Where is it? Well, let's think more about these electrical transformers. So actually, I need to go back to the PowerPoint slides. If you'll be a little patient with me here. So it turns out, okay, here actually it shows a slide where I identified those spectral peaks as we just did. So here, this is just a highly simplified transformer core diagram. So there's an iron core, and sometimes that's called an iron ferrite core, and sometimes it's made up of laminates. So there's a primary voltage, and then there's a secondary voltage. And what happens is magnetic flux gets set up. There's this rotating magnetic flux that gets set up inside this ferrite core. And it turns out that anytime there's changing magnetic flux or changing electromagnetic fields, that can actually affect material. And the material can actually output a sound. And that sound is going to be called by the name of magnetostriction. So what's happening with this magnetostriction is that the iron core is actually undergoing mechanical oscillations. So our iron core is undergoing mechanical oscillations in response to the oscillating electromagnetic field. So when the core undergoes its oscillations, this core, it's expanding in volume and reducing in volume. As it does that, displaces the air molecules, the adjacent air molecules. And then that's how the resulting sound wave is generated. It's those air molecules are being displaced, and that energy turns into the oscillating acoustic signals that then propagates as a longitudinal acoustic wave. So what's going on here? There's sort of a mystery, and maybe some of you can figure this out already, but I'll go ahead and I'll tell you what's going on. So this is just a very crude diagram of magnetostriction. So I'm going to say we have a magnetic field, and I'm just going to call it north and south for the two amplitudes here. That may or may not be correct, but you get the idea. Then we have time in seconds, and this is just one cycle of oscillation. So we have one cycle of electromagnetic oscillation. So as the field goes from its neutral position and heads northward, that core is expanding. The core expands for the transformer ferrite core, it displaces air molecules. And as that happens, sound is generated. Well, then the field reaches its peak, and then it heads back towards its neutral position. The core contracts as we go back to neutral. Now the magnetic field is heading south, and as it does that, that core is expanding. Reaches a peak value, the core starts to contract. We go back to the neutral position. So what this is saying is that there are two mechanical cycles for every one electromagnetic cycle. So 2 mechanical cycles for every 1 electromagnetic cycle, and that's called magnetostriction. So that's why for our data, we don't get a 60 hertz audio signal, we get a 120 hertz audio signal, and integer multiples thereof from the 120 hertz. So that's just an interesting little thing about magnetostriction. I think I'm going to just take a little side deviation here. Do you remember earlier on we took a look at a tuning fork data? So let's see if we can go back to our blog and type in tuning fork. Let's see what we have here. In the very first webinar, we took a look at tuning forks. And we looked at a tuning fork sound file. We looked at the data. And one thing I told you about the data was that data had a steady state excitation and a steady state response. Well, how could you excite a tuning fork into steady state response? And actually what we're going to have to do here is go to the vibration data, and we're going to go to tuning fork in the search box. So we're at the vibrationdata.com website. And before I did my blog, I did a lot of newsletters. And I haven't really been doing those newsletters lately because I've been doing the blog instead. But these newsletters are still available for download. So how do you excite a tuning fork into steady state? Well, if we take a little electromagnetic coil and drape it over one of the forks or tines and apply an oscillating sine function, we can actually excite the tuning fork into steady state response. So you could say a resonant response. So there's a little better view of it. So what was the frequency of this tuning fork? Well, if you remember from previous exercise, it was an A note, and it was at 440 hertz. And actually, I have a little note to myself here that as measured, it was 442.4 hertz. And of course, due to manufacturing tolerances and so on, it wasn't exactly 440 hertz. So in order to excite this into a resonant response, I had to dial in on my analog function generator 1/2 that frequency, so 221.2 hertz. That's what I dialed in, and I applied that voltage signal, or you could say that current signal, to excite the tuning fork into its resonant vibration. There's a waterfall FFT of well, that's something different. That's actually where we've excited the tuning fork with an impulse force. Okay, we'll cover waterfall FFTs coming up in the next unit after this one. But here was the sound pressure, the tuning fork driven by the coil, and you can see it's a fairly steady state response there. I also play around. I took a threaded rod and just wound the electromagnetic wire around the rod, and it was a 36-inch steel rod, and the sound pressure came out to be 2600 hertz, and that's actually the longitudinal vibration mode of a 36-inch rod made from steel with free boundary conditions. But in order to excite that resonance response, I had to actually excite that rod at 1/2 that measured frequency, which was 1300 hertz. So 1300 hertz was the actual input voltage signal or drive voltage signal. Okay, but let's go back to the now to the slides here. So we've covered magnetostriction, and let's see what else we have here. Maybe one or two others before we call it a day here. So we also have, Hoover Dam. We got two things. We've got Hoover Dam, but before we do that, so here's one of these little regional turboprop aircrafts, a Bombardier Q400 turboprop. And I was actually flying on one of these, similar to the one shown, and it just so happened my seat assignment was such that I could look out over the spinning turboprop for one of the engines, and I made a recording on my cell phone recorder, and I was able to record the sound. So here we have a Bombardier Q400 turboprop aircraft. It has two Pratt & Whitney Canada PW150A turboprop engines. Now the engine propeller rotation rate during takeoff is 1,020 RPM. But then the aircraft is throttled back, the engines are throttled back at cruise to 850 RPM, and that's equal to 14.17 hertz. So that is going to be the cruise altitude turboprop hub oscillation frequency, or rotation frequency. Well, there's 6 blades, so we're actually going to pick up the audio signals at times 6 multiples, so our blade passing frequency, this turboprop, at its cruise altitude is 85 hertz. So let's see if we can take a look at some data here. So I'm going to type in the word vibration data here, and we'll just go ahead and take the FFT directly. So it's going to be an ASCII file. It's going to be called q400.txt. Mean removal, yes. Handing window. 500 hertz, is that good? Yeah, we'll say 500 hertz. Again, unscaled sound pressure. So we calculate, not interested in phase. Let's look at the time history first. So this is the time history, and this is the unscaled sound pressure. And actually the data was actually clipped a little bit, but we'll just make do with the data. And due to some filtering, it doesn't appear perfectly clipped, but it was clipped data, slightly clipped. But you can see there is some pattern there. It looks like a pattern of some sine functions there, so somewhat repetitious. And we get better idea by transferring that data, transforming it into the frequency domain. So here we have our Fourier transform magnitude, and we have our spectral peak, our first major spectral peak at 85 hertz. So that's the blade passing frequency at cruise. And then we have a times 2, times 3, times 4, times 5. Also, just a little footnote, I was inside the cabin when I measured this data. So the cabin walls were filtering the data. So that might have affected the relative peak amplitudes. But you get the idea here. We get a nice pattern of spectral peaks because we have 6 blades times the hub frequency, the hub rotational rate of the turboprop engine at its cruise altitude. So that's just a little fun thing to take a look at. A lot of times we like to do launch vehicles in this series of webinars, but we also take an occasional look at aircraft and transformers and other fun things as well. Okay, our last data we're going to look at for today is Hoover Dam. And I've got a funny slide. It's kind of funny, but it's also kind of serious too. Let me show that to you. You know that you are an engineer when your favorite part of your Las Vegas trip was the Hoover Dam tour. And the last time I was in Las Vegas, I didn't care for all the glitz of the strip. The bright lights, all the gambling, whatever happens in Vegas stays in Vegas. All that stuff I just don't care for. But I did really enjoy the Hoover Dam tour. So here's Hoover Dam, and the Colorado River snakes down and forms the border in a certain section between Nevada and Arizona, and then between California and Arizona as well. And I lived for Arizona for most of my first 50 years. So here's these turbine generators. So even though we're post 9/11, the Department of Reclamation that runs Hoover Dams actually has guided tours that you can go down and see various features of the dam. So right here we're deep inside the bowels of the dam, and we see these turbine generators. So these take the water, the power from the water, and convert it to electromagnetic power that's then fed through transmission lines and sent out to the various localities onto the power grid. It's interesting that the way the different power companies are all linked together in terms of transmission lines, and they buy and sell power to and from one another. So here's the sort of the underside. So the top part, you see the electromagnetic generator, and underneath that level, here we have the turbine shafts, and then the shafts, each shaft is 65 feet long, or 19.8 meters tall. The diameter is 38 inches, or almost 100 centimeters. So here's just sort of another kind of black and white grainy image. So it turns out there's an exciter on top of these, and that's used to sort of energize the magnets. And so we have the rotor here, and then there's magnets, and then there's stators, both in this portion. The stators remain stationary, and then the electromagnetics, excuse me, the magnets actually rotate with the rotor. Then we have the shaft, and then we have the turbine section here. And it turns out that the water coming through is 60 miles per hour speed, and that causes the turbines to rotate at 180 RPM. Well, it turns out there's a number of different turbine designs and models within the Hoover Dam. And the most common one, there's 9 units that have 15 vanes. That's the turbine vanes down in this portion. There's 5 units that have 16 vanes. There's 2 units that have 17 vanes, and 1 unit with 19 vanes. There's actually 2 other smaller turbines as well, but these are the main 17 primary turbines. So let's take a look at what kind of acoustic noise that these turbine generators actually generate. So we can actually look at this data. Here's the plot, but just for practice, I'll show you how to call this up. We go to vibration data, so we're down here, vibration data. Just take the FFT. This will be hoover.txt, so I'm just going to type in hoover.txt. Mean removal, yes. Do a handing window. We're back to unscaled sound pressure. We have no idea what the decibel level is. That was not measured. Plot up to maybe 200 hertz. Calculate. Ignore the phase angles. So here's our time history here. Let's zoom in. Well, somewhat random, but possibly with some distinct sinusoids buried in that signal as well. In fact, here you can see there's different spectral peaks that occur. Now, we're not going to be able to identify all those spectral peaks. That's not going to happen because I just didn't have enough information. And as I was recording this data, the security guards and the trained cameras on our tour group, the security people were gracious and let me do some recording, but they kind of let me know that they wanted me to move on as well. So I didn't have a whole lot of time to take all the measurements that I wanted. But I was able to identify some of the spectral peaks, and I'm just going to go back to the slides to show you these. So in this case, I'm only going up to 100 hertz, so rescale the plot a bit. So Hoover Dam turbine generator, sound spectrum, unscaled sound pressure, frequency in hertz. And I went and using data cursors, identified some of the frequencies of those spectral peaks. So the next question was, how can I make sense of those numbers? What did those represent? And this is actually the same data, only I'm showing it out to 400 hertz. So this plot allowed me to identify some higher frequencies as well. So I was able to identify these peaks, and actually I want to show you something here. I was able to determine from published data that, again, 180 RPMs, that's the shaft speed of those rotors. That's equivalent to 3 hertz. And there's either 15 or 16 vanes for at least the first 2, the primary model and the secondary model. So let's go back to our friend vibration data again. And let's see what we can do. If we go to rotation here, and we have turbine generator frequencies, that's another little utility. So I could type in 180 RPM or just 3 hertz. So there's either 15 vanes or 16 vanes. We could also type in the number of poles. I don't think I had that information, or maybe I did. In fact, we probably at this point, I need to re-educate myself and go back and say, there were 40 poles. Okay, I should have noted that there was 40 poles for our generators. So this gives me a table of numbers. So 3 hertz is the rotor speed. 45 hertz is rotor speed times 15 vanes. 60 hertz is 1/2 the rotor speed times 40 poles. 90 hertz is 2 times the rotor speed times 15 vanes. 120 hertz, rotor speed times 40 poles. That's interesting. It's also the magnetostriction frequency as well. 135 hertz, 3 times rotor speed times 50 vanes, and then so on. And of course, we also have to account for some of the models at 16 vanes, so we can run those numbers as well. And that's basically what I did. So going back to the PowerPoint slide then, this is as best as I was able to do. These lower frequencies, I don't know what they were. Maybe some of you can help me out. But I was able to identify some of these measured spectral peaks in terms of what their descriptive labels were. So that's just for any of you that have a civil engineering background or an electromagnetic background, or you've done different machinery diagnostics or continue to do so. This is kind of interesting, and it's real interesting. Whenever you're on travel or you're on a family vacation or you're on a business trip, whatever, you know. And of course, nowadays we all have cell phones. Our smartphones have little built-in data recorders, and maybe their sample rates aren't as high as we want, but we can do some digital audio recording just about wherever we are. And I will sort of throw out a little caveat. Not every sound you measure has interesting spectral peaks. Some sounds that you might measure from, say, a waterfall or something, it might just be broadband random. And taking a fast Fourier transform or Fourier transform of broadband random vibration, it's not going to be very interesting. But every once in a while, there is something like a turboprop aircraft or a Hoover Dam turbine generator, or just that ugly-looking utility box in your front yard or your neighbor's front yard that does output some sinusoidal oscillations due to some sinusoidal vibration of sorts. And so when we can find those sorts of signals, that's a happy day because we get to play with the data and go in and try and figure out what was going on with the data, identify the spectral peaks. And in the launch vehicle for my NASA people, when we look at launch vehicle data, we've already talked about how sinusoidal oscillations can happen in launch vehicles. We might have for a solid rocket motor, there might be a thrust oscillation, or for a liquid engine vehicle, there could be a pogo or some combustion instability. So we do see sinusoidal type things in our launch vehicles as well. So the FFT and the Fourier transforms are good tools for resolving frequencies. Now, sometimes these spectral frequencies shift with time, and that's our next unit, which is going to be waterfall FFTs. Again, I encourage you to kind of go through these exercises and do the Apache helicopter on your own. Go through these exercises. The file names are duly noted in the PowerPoint slides. And again, you can just go to the vibration data blog, and you can pick off those data samples here. Now, here's a previous unit. So if we just type in webinar, and we go to just do a search there, go to FFTs. I think I showed this to you before, but just as a reminder, pick up the data files here, and also listen to the corresponding audio files as well, because those are interesting. And for the turboprop, I actually have an audio-visual file that you can look at as well. But that's all for now, and everyone have a good day, and thanks for your participation in this series of webinars. So goodbye for now.